Okay, hi. This video will talk about the potentiometer circuit, and generally what the potentiometer circuit is a bit like a potential divider circuit, but the only difference here I guess is just that you have a wire. Okay, so having a wire is in the potentiometer, and you have a slider where you can adjust the potential. When I say adjust the potential, meaning by changing the length xt, you can take different portions of the wire to portion out a certain potential that you need for a particular experiment. So let us look at the circuit first and see what kind of setup it needs to be called a potentiometer. So step 1, you need a driver circuit. So the driver circuit is the circuit that is connected to the wire, and it's like the constant lah that is always there. So the one that I'm highlighting is actually the driver circuit. Okay, so it consists of E1, which is the driver cell, and all the way including the wire XY. So the wire XY is like how should I put it? It's like the main character. Okay, I'm trying to, there we go. So wire XY is the main character, so to speak, and you will normally be given a meter long lah, and it will be a wire of uniform diameter. Okay, so a few things to note is that when I change the length of the wire, I will change the resistance in proportion to the length. So if I double the length, I double the resistance. All right. Here you will find that between the jockey and the ammeter, I can put whatever I want. This meter can be an ammeter, can be a voltmeter, can be a galvanometer. So in between the two yellow points, or in place of E2, is whatever I want. I could put a battery there. I can put a part of another circuit there. Basically, the idea here is that you can use this setup to measure anything you want. Sorry, any potential between AB. Okay, so this thing works like a potentiometer or a voltmeter. It's a bit like, now you have to measure the potential difference between 2 points. So how do you MacGyver, so to speak, or come out with a rudimentary potentiometer circuit such that, hey, you are able to measure the potential between 2 points just with another battery and a wire, and if you need a resistor and a way to measure the length. So if you're Iron Man and you are caught in a cave and you need to build your Iron Man suit version 1, how do you actually build a voltmeter so you can measure stuff that you need to measure? Well, you just need a wire and a battery and just this thing. Because we actually don't really need a reading for this meter. We just need to know whether there is reading or not. Okay, so let me continue writing down first. So this will be used to measure any potential between the points A and B. Okay, so this point AB, I can connect to any circuit I want. Okay, any circuit I want. All right, so point number 3, the potential difference between XY, this entire wire, okay, because it is in series with R. So it is spread, it will be shared with R and spread evenly across XY. Okay, so for example, if let's say the potential difference of XY is 10 volt, okay, then every 10 cm is 1 volt, because 100 cm 10 volt, 10 cm 1 volt. Okay, and this shows you the second strength of the potentiometer, whereby it can be very sensitive. Small division. All right, so let's continue. Okay, so and finally, number 4, you can use R to adjust the sensitivity of the voltmeter in particular of the potentiometer. Okay, so there's a few working principles. Number 1, we will adjust the length xt until the voltmeter or galvanometer reading is 0. Okay, so this is what I mean by you don't really need a sensitive meter. You just need to know whether there's current or not. So you just need a meter to tell you whether there's deflection. by adjusting the length. Okay, so this adjusted length is called balance length, okay, when the voltmeter reading is 0. Okay, so the second thing about us doing this is because when the voltmeter is reading is 0, there's no current flowing through the loop AXTB. This part, there's no current flowing. Okay, that's why a voltmeter is like it's like Gandalf, you shall not pass. So if the voltmeter has no reading, it means that the potential difference across XT will be equal to the potential difference across AB. No potential difference, no current flow, because no energy no gravitational potential difference, things will not fall. So you need high potential to go to low potential. If these two potential are the same, marked out here, then your voltmeter reading will be 0. So this is how that reading is being read. By changing the length, I can see that, use ratio to find the potential between XT, and that would be the potential difference between AB. Okay, so now we can look at a example. Okay, so here, right, you have a power supply and a solar cell. Okay, and you can see that this itself is the driver circuit. All right, this thing is the driver circuit, and the galvanometer is here. So its purpose is to measure the potential difference of a solar cell. All right, EMF produced by the solar cell is measured by the potentiometer. Potentiometer wire is 100 cm long and has a resistance of 5 ohm. Power supply is 2 volt. Okay, and the solar cell has an EMF of 5 millivolts. Like most solar cell, the potential difference will be quite low. All right, and what value of R can be used so that the galvanometer reading reads 0 when the length PS is 40 cm. Okay, so if this is the driver cell and the galvanometer reading is 0, that means the only way for the current to flow is this loop that I labeled. Current cannot pass here. Okay, you shall not pass. Cannot. All right, and what will happen now is that there are a few ways to do the question, and like normal in my first example, I will show you all the methods because I believe in full disclosure. Yay. You know, true talk, guys. True talk. Must tell everything. Don't cancel me. Joking lah. All right. Cancel culture is quite toxic, right? Anyway, now, right, if this is 5 millivolt, I guess the first thing, so you might be wondering, Miss, isn't there a lot of equation? I heard there's a lot of equation. Look, I love one equation and use in many places. So I prefer to be multi-purpose lah. There's a main idea, and if I can, I want to use the circuit concepts to solve the question rather than memorize a new equation. I am team no memorize if can, okay? If you really need to memorize, I will let you know. All right, so in this case, right, we have already established that since the potential difference is 0, the galvanometer reading is 0, so there will be no potential no potential difference between PS and the solar cell, i.e. PS will be the potential of the solar cell, and that will be 5 millivolt. Okay, so I guess what remains to be done is that since the current will flow this way, the question here would be, how should we move forward? You know what to do? UV equal to IR lor. Since there's a loop where the current is flowing, I'm just going to do it for the yellow loop. This is 2 volt, okay? And then I notice I got too many unknown. I don't know the current. I know the entire wire is 5 ohm and the external resistor is R, so I cannot find R without finding I. Then you might be thinking, snap, what do I do? Well, let's consider using a different method, which is called ratio. Okay, so this will be the first method. This one is the instinct. We park it one side first. So if you want to use a potential divider, right, then you know that this 2 volt is kind of like there's some form of sharing of the potential between P and Q. So it's spread evenly across PQ. So if 40 cm is equivalent to 5 millivolt, then the entire wire, because PS is equal to solar cell 5 millivolt, the entire wire, 100 cm, would be Ratio is your best friend. 12.5 millivolt. Okay? Get it? Get it? Get it? Okay. So the potential difference from P to Q will be 12.5 because the potential difference between P to S is 5, and we know it's 5 because it is the same as the solar cell. All right. So hence, we will use the potential divider method. Okay. So you know PQR is in series with PQ. So the 2 volt is being shared between R and PQ. Okay. So here you will find that since the potential difference, wait need to move my mouse a bit. Why can't I move my mouse? Okay, there we go. All right. So here, since the potential difference, VR ratio VPQ is equivalent to R ratio 5 ohm. Okay. So this R and PQ is in series. It's a bit like the potentiometer in series lah, the previous video. Okay. So you take 5 over 5 plus R because 5 plus R is the total resistance in the branch. And the potential that you know is PQ. So the resistance of PQ is 5. So 5 over 5 plus R times 2 because you're sharing 2 volt. And the resistance across PQ would be 12.5 millivolt. So what you need to do is just complete the calculation. All right. And you will get 62.5. I mean, I'm just cross multiplying lah. All right. And finally, your value of R would be 795. Okay, so this is one method. Using ratios, you use ratio 2 times. First time is using the wire to find the potential difference between PQ. Okay, second ratio is to use potential divider method to share the potential between R and the entire wire PQ. All right, here's another method. Since you already know that PQ is 12.5 millivolt, you can use V equal to IR for the wire PQ to find I. Remember, we didn't use this because we don't know I. So now we can find I with just the wire PQ because you already know the potential difference of the wire PQ. So I here is 2.5 milliampere. Okay. Then you can use V equal to IR for the driver circuit. So 2.5. The whole circuit will be R plus PQ or R plus 5. All right. And this would also give you your 795 ohm. So this method still needs you to do the ratio. 40 cm is 5 millivolt. 100 cm is 12.5 millivolt for the entire wire. Once you have the 12.5 millivolt, you will apply V equal to IR on the wire PQ to find the current in the wire PQ, and then apply V equal to IR for the entire circuit to find the value of capital R. Okay? So a slightly different method that another person could employ is, let's say the potential difference between PS is equal to the IPS, RPS. Okay, so what I mean here is that you know the potential difference between P to S is 5 millivolt. So you can put that in. You want to find the current first because with the current you can do this, right? So then you use ratio for the resistance. So the resistor wire, right, is 5 ohm for 100 cm, but from P to S, because now we're taking the potential from P to S, so it will be 40 over 100 times 5. Okay, like 100 cm is 5 ohm, 40 cm is how many ohm? That question lah. Okay, so then you will get your I as 2.5, and then after that you can just use this equation, the driver circuit equation, to do the thing. So you might be asking me, wow, miss, so many ways, many roads to get to Rome. Okay, so what I mean by many roads to get to Rome is that it's a freestyle kind of question. Many way to make a laksa, you know. So you can use potential divider method. Okay, always valid because you have two resistors in series. You can use V equal to IR, or also known as Kirchhoff's second law. V equal to IR is Kirchhoff's second law because this one is One closed loop ma, so sum of V is equal to sum of IR. Okay, so when I use Kirchhoff's second law, I must make sure that I need to have some potential. So when you have that potential, you could either, number one, use the potential of PQ to find the current, and then use the current to find the value of R. Okay, so basically applying V equal to IR for the wire, and then V equal to IR for the whole thing. Always works one, okay? Other way that you can do to find I, if you don't want to go through a 1, 2, 3 step process, is to do this. Just instead of using the entire PQ, which you did here, you only use from P to S. So you can apply V equal to IR again for P to S. Because PQ is 12.5, then you use PS law, 5 law. Same current ma, is the same wire. Okay? There's only one current because there's only one loop. So you can just apply ratio to the resistor. You can apply the ratio to the resistor. You can apply the ratio to the potential. Okay? So when you do this, you can find I. So there's only one step here and two step here. It will be a two-step question. Alright? So it is not difficult. It just sounds very long-winded because I'm teaching it from scratch. Okay? And the second thing about this question is that there's no one fixed way. So different book you open, different notes, different teacher will tell you different things. I prefer to tell you everything or show you the different methods. Whichever one you like lah. Go and try it out a bit. You will kind of see which one you are leaning towards. I prefer to use V equal to IR lah, but some students much prefer to use ratio. Just make sure you ratio correctly lor. Okay? So that would keep the answer as 795. Okay? So that's the second method. So let's look at a structured question now. First part, state Kirchhoff's second law. I just state already. So I write again now for you. Okay. So Kirchhoff's second law states that in a closed loop, the sum of the EMF is equal to the sum of the potential difference across every component. Sigma E is equal to sigma IR. And it follows the conservation of energy because EMF provide battery, EMF provide energy, and then IR uses energy. So EMF is non-electrical energy to electrical energy, potential difference, and IR would be electrical energy to non-electrical energy. Please refer to previous videos of the chapter. Alright, let's continue. So now you have a circuit, and basically the examples I choose is level 1 one. You should go and find the level 2 questions in your past years. Alright, the same thing, I just slot in a battery between the 2 points. This entire thing, besides the battery E or cell B, is your potentiometer. Okay, so my point here is that if you are doing this question, it's good to identify a potentiometer and also to understand that there's no fixed circuit. Please don't go memorize anything. Nothing to memorize here. Okay, you can see here. Never mind. Let's continue. So you have a uniform wire XY with a length of 1 meter, resistance 4 ohm. Cell A has an EMF of 2 volts, internal resistance 0.5 ohm. Current through cell A is I. Cell B has an internal resistance E. So I'm going to label all of this first. Uniform wire is 4 ohm. Okay. And the current through cell B is made 0 with the movable connection J adjusted. Okay. And such that the potential difference of the variable resistor is 2.5 ohm. Okay, not potential difference. The resistance of the variable resistor is 2.5 ohm. Okay, so now this question, you are internal resistance. And when you ask to apply Kirchhoff's second law, right, you want to use sigma E, sigma IR. They are a total of 1 internal resistance, 1 R. You are using this loop. Okay, so 0.5 ohm is a 1 resistor. X to Y is the second resistor. Don't forget this wire XY has resistance. And this variable resistor is 2.5. So you should sum all of them up together. Okay. Then you can find your I law. Your I is 2/7. 0.286. Do not leave your answers in fractions, my friends. Not allowed. Okay. calculate the potential difference across the length xj. So you can use V equal to IR, but xj is 0.9 meter. It's the same I, okay? So if ij is 0.9 meter, but the whole wire is 1 meter, and 1 meter is 4 ohm, so 0.9 is how many ohm leh? You can use ratio, or if you know 3.6, you just put 3.6 inside, it's only 2 marks. Okay, then you get the answer 1.03 volt. Use your answer in part 2 to state the value of E. So to find the value of E, okay, you will just equate it to this one, 1.03 volt. And then if you ask to state why the internal resistance does not affect, it's not required to determine E, well, I would say you look back to the circuit. Where we go, okay? So if there's no current flowing through here, there will be no lost volts. No lost volts meaning what I am measuring between X and J is the terminal voltage. And the purpose of the experiment is to determine the value of E, or aka the EMF, aka the terminal voltage when there's no current flowing because there's no lost volts. Okay? So because of this, you can immediately tell that if there's no lost volts, there's no current flowing, so you do not really need to know the value of the internal resistor. Alright? Okay, so no current flows in cell B, hence there are no lost volts in the internal resistance of cell B. Okay, so that would be the structure question. You can find slightly more complicated ones. I will leave that to you because every circuit is like a nice box of chocolates. You don't know what you're going to get, so please go try them. Alright. Okay, so this ends the calculation portion of potentiometer. Watch the second video where I talk about some conceptual questions of potentiometer. So see you in the next video then. Bye-bye.